Since my topic is real world data analytics, I'm going to use a lot of real example to explain what data analytics in the real world look like. Okay. So I quote some word from SAS, the one of the very, very long established company. Data analytics examine data to uncover hidden pattern, correlation, and other insights. It's much more efficient than traditional business intelligence due to the quantum jump of machine power. Today, we can do so much computing in such a short time. It makes machine learning much more practical. Another thing happened in the last few years is that the pervasiveness of big data. There's so much data, this data enable realistic statistical analysis. You want to do real analysis, you need the data. You want to do good machine learning, you need the data to come up with the pattern, to learn the pattern. So to some extent, this data analytics and the current renaissance of AI, artificial intelligence, they are part of the one influence the other. One, it's actually part of the AI renaissance. So with such a powerful machine learning and the big data, there's a lot of great story come out of this combination. The first one is Watson system in 2011. It beat Jeopardy champion Ken Jennings and Brett Rutter. The two of them, that they win $5 million, never lost. Watson beat them because Watson have a computer system with access to 200 million pages of data, structured, unstructured. So they can learn a lot of things. So when doing the competition, they can be able to give an answer very quickly, right away. Another example everybody know about is the AlphaGo, based on artificial neural network, deep learning. Defeat Lee Sedol is the world champion from Korea in the game of Go, 4-1. After this, everybody, wherever I go, people talk about AlphaGo, deep learning. Deep learning is also wonderful, very good at image classification. In the old day, the algorithm has been developed for a long time. In the old day, you probably can do 1 level, 2 level of artificial neural network. That's, take up a lot of computing power. Today, with GPU, you can do hundreds of layers or maybe thousands of layers. You can do real-time facial recognition right away. So again, deep learning is wonderful for this kind of application. The question is that these are all great headline grabber, but there's issue. The two issues face machine learning. The first issue is that the laboratory part, in order to do the machine learning, you need all this data together. So the machine can try to see the pattern, try to learn the pattern from those data. The process of getting all this data together, it's very, very difficult, a lot of work. Most people won't talk about it because this is the dirty part, the dirty work of the machine learning. Another one is that what kind of machine learning algorithm among all these many choices is most suitable? Is deep learning, is artificial neural network the choice for all the problem? So this is the two issues facing machine learning. Let's take a look at the first issue, is that a typical machine learning process, you scope out the problem. Where's the pointer? Where's the pointer?
This one is the pointer, center.
Oh, okay. Sorry. Okay.
So on LED you don't get it pointer, so this is LED.
Okay.
You can quantify.
Oh, yeah. Okay. Sorry. So you scope out the problem, then you have to get the data, clean the data, extract the data, load the data into some data warehouse, and then you finally do the sexy part, which is the actual applied machine learning to try to extract the pattern, data analytics. And then after you get the result, then you try to interpret the result. If the result is not what you're looking for, or you don't get the kind of pattern you want, you go back and start the process, get more data, get different dimension, get different feature, and then build another data warehouse in order to go through this process. This whole process, especially this part, consume a lot of effort, a lot of time. And this is the part that most people don't talk about it. And this part, traditional way, way is that you use the data warehouse. This is a traditional ETL data integration process, building data warehouse. A data warehouse, most people here are very familiar with. You use the relational structured database and used by 80% of enterprise and analytical BI user. The problem with this is that it's very expensive to build. After you build it, it's very difficult to change and fix data analytics, rigid and slow. If any time that you want to go back to add more data or change some data, it's going to cost a lot. And these have a significant consequence in many of the real world projects. One of the greater examples, my exhibit one, case one, is the expensive proposition, the Watson and MD Anderson. MD Anderson is the most advanced cancer research center in the US, part of the University of Texas, Austin. They probably also is the world's biggest, the most advanced cancer research center. About 5 years ago, the IBM Watson made a proposal to develop something, oncology expert advisor for cancer treatment. Basically is that spend 5 years and $62 million. Basically, they want to take all these patient data, use machine learning on the patient electronic medical record to learn the ultimate treatment strategy for individual patient. Now, many times, when you have a cancer, you go to the doctor, oncologist. What the oncologist says, you pull out the NCI protocol. There's about 10, 20 different kind of protocol, different medicine, different dosage, different regimen. And then the doctor will say, well, let's try this first. And if this doesn't work, we try the next one. By the time you try the second one, you die of side effect. Most of cancer patients that die of side effect not from cancer itself, because a good doctor means that a good doctor has seen enough patients. So when you come and you say, yeah, for your situation, probably the best is try this protocol. So what this project is supposed to do is that to learn from the electronic medical record of all these patients from MD Anderson and try to see if they can draw a pattern for this kind of patient, this kind of background, this kind of disease, these kind of things. What kind of treatment protocol works best for this patient? And in fact, the initial prototype worked very well, achieved about 90% the prediction accuracy. Basically, this system will recommend, say, for this patient, I put in all this data about the patient into the system. The system will say, for this patient, the best treatment is this. And 90% match the expert doctor, the opinion of expert. So it's great success, except there's a problem. It takes a long time to integrate all the electronic medical record to the same platform, because there's no standard way to recall the heart rate or blood pressure or glucose value, even bedside temperature. There's different way to label, to store that information. You need to get all this information together in order you can apply machine learning to abstract a pattern out of it. When MD Anderson changed their electronic medical record from clinical station to Epic is one of the big ones, during this 5 years period. And then all of a sudden, the whole existing data warehouse no longer works because it's a fixed schema. The new data schema will not be able to move into the existing data warehouse. Also, the new drug protocol and the clinical trial data over the last 5 years need to be incorporated into the data warehouse in order for system to be pilot again. And so when they go back to University of Texas, Austin, and say, no, I'm sorry that the system needs some more money to rebuild the data warehouse or change the data warehouse. And the University of Texas, Austin say, we spent 5 years, $62 million, it's enough. We are not going to spend more money. So they set up a committee to make an audit, and all this information I present here is actually come out of the audit report. So project totally suspended in March 2007. In this case, the problem is not the machine learning. The machine learning do a great job. The initial prototype actually predict 90% accurate, the same as the expert doctor, except they spend majority of their time, majority of the money, try to build up this data warehouse, to integrate all this data together. And when MD Anderson changed their electronic medical records from clinical station to epic, and everything fall apart. And that's again it's not machine learning's fault. It's all this plumbing, all this dirty work that's problem. Why such difficulty? Just look at the typical electronic record. A patient like this, this guy looked like has got a lot of problem. So before he go into the hospital, he had to enter his medical history. And then if he wear some kind of smart device, his daily routine, his heart rate, his whatever information, his genetic, his DNA, his genetic background, his family history, if he wear any kind of implant device, the implant device will spill a lot of data. All this information are valuable, are relevant if you want to, do a machine learning on, try to find a pattern. If I go to hospital, a lot of information in EPIC system, in the hospital information system. Go into ICU, you plug into all these machines. Every machine spill out information like mad, or all kinds of digital information. You get a blood test, you got blood test result, you got your EKG, your ultrasound, your pathology. If you have some biopsy, pathology result. The medicine you take, the other device that you have, all this information, some of them, many of them are relevant if you want to draw some kind of conclusion, extract some kind of pattern. And this is a humongous data integration problem. You need to integrate not only both data schema, but also data semantics. So I want to emphasize here data semantics. That's one of the biggest problems with today's data. Most of the data, whatever data we see. What do I mean by data semantics is that typically in a relational database schema, except a few key, most of the data entity are character string. You look at some of the data dictionary, it's all character string without data semantic, no linkage between them. Now, what do I mean that no data semantic? Give you a simple example here. This is what you see the people describe in different electronic medical record. They talk about diabetes. So I zoom in that. This all diabetes. If a person look at this, they say, yeah, I know this is all diabetes, but computer have no idea this means diabetes. It's 100 different kind of disease. So in fact, all what we store in our electronic medical record, it's the information for the human, not for the computer. It's a character string that require human to interpret. They look and say, yeah, I know this is diabetes, but computer look at it, they have no idea. This could be all different kind of disease. Even if you use coding to represent diabetes, depends on what coding system you use. It could have a different number. Here you have 7, or the one I highlight there is that they all represent the coding from different medical language system, different taxonomy. They have different coding system. And then so you have to get all these things to work together, to integrate together. So one of the ways of doing that, so that's why the new data integration scheme is called new data lake, because if I want to build the data warehouse, it becomes so rigid. Every time I make a change, the whole thing breaks apart and rebuild it. So why not just put all the data in one place? And then whenever I need whenever I need to do data analytics, I do the ETL at that time to build a data map for specific for the analytics. And now you got some flexibility, but it's very expensive because every single time, if you want to do analytics, you have to build a data map, and that's a very expensive proposition. So what Gartner says, without data semantics, the data lake literally is just a data swamp. It's a collection of disconnected data pool or information silo all in one single place. And so without data semantic, you cannot get all these things to talk together. So a better integration approach is semantic data model. Basically, it's a semantic data model. I'm going to go through some detail here. It's basically a key element of semantic data model is URI and RDF. And there's many other things. I'm not going to go through the detail, but UI, RDF are the key things for the semantic data model. What do I mean by UI? As I mentioned before, all these represent diabetes. That's for human. That's a label for the human. But internally, we need to be able to represent this concept, this diabetes concept, with some unique identifier. And that's from W3C recommendation. It basically says that the uniform resource identifier, URI, they recommend that this is the way you identify that unique concept. For example, the diabetes. You started with organization URI, and then with your internal coding for the diabetes. If you define the URI, uniform resource identifier this way, there will be no ambiguity. No matter where you send it to, globally, it will represent diabetes. I mean, the question is that, well, everybody define their own URI, we get back to the old problem. The nice thing is that over time, there will be de facto URI show up. For example, if I'm doing life science research or doing medical research, I'm going to use the URI come out of the National Institute of Health, so I can plug into all the knowledge they have built up in there. I don't want to create my own URI. Over time, they will be de facto. And true enough, after the last 5-10 years, there's a set of de facto URI everybody follow. And slowly, everybody will converge to certain representation. And that represents a unique concept. Now, we have something called UI to represent diabetes. All the other thing is just a label. You can have 100 label, 200 label, doesn't matter, for different languages, no problem. That's just label for this concept. Now we can uniquely define the concept, then we can start building the ontology. You heard about ontology, basically is all the property, all the attribute, all the relationship between all these unique concepts. Then we can start building, because now there's no ambiguity. I know what I'm talking about. This thing is a diabetes. There's no question about that. And the language you use to describe this property, this attribute, this relationship is a language called RDF. RDF stands for Resource Description Framework. Did not say it here. It's a uniform way for information representation. It's out of many, many years of knowledge research. Basically, it says that any information, any knowledge, if you want to encode, you can represent it with this kind of format, resource description framework. Basically, it's a subject, predicate, object. For example, in this case, diabetes mellitus, the contraindicated drug, the drug that you should not take is the sodium dextrose. And then sodium dextrose, its a mechanism of action is sclerosing activity. The reason you have diabetes, you should not take this drug is because it will harden your blood vessel. And since we use UI for sodium dextrose, these two triple will connect together. It will automatically connect together. And I have done many consulting projects for the last 10 years in this area. I haven't found a case, doesn't matter in intelligence, in anywhere, I haven't found a case that I cannot model with this kind of simple representation. And most important, it's a W3C standard. So basically, is that if you do this, then many tools that you can use to read this there, to store this information. And with RDF, UI and RDF, you actually connect to a graph. An example I just showed previously, the diabetes, the contraindicated drug, medicine, sodium dextrose, the mechanism of action is sclerosing activity. So eventually, it will connect to a graph. As long as I use the same URI, all these triple you throw into the bucket, it will connect. Throw into the bucket and connect. So with this kind of mechanism, all the EMR silo, I do ETL, extract, cleanse, whatever I need to do. I map it over to whatever entity. I map it over to URI. Transform all the table, all the whatever data format into RDF. RDF is the most universal way of representing information. So it doesn't matter where the information comes from. You can map it over to URI, RDF. You create EMR, the electronic medical record semantic database. And the most important thing is schemaless. It's totally schemaless. And since it's schemaless, this EMR can change. You can change from clinic station to Epic. You can add more information. You can do whatever you want. And no need to change this semantic database, because you just need to add things to it. And since there's no schema, it's very flexible. Anything you can put in there. With this kind of algorithm, with this kind of approach, you do one-time ETL, You put everything in the semantic database, and then after that, every time you want to do analytic, you can just go there and extract the pattern, extract the feature, extract the dimension, create a table, fit into a machine learning algorithm. You'll give you some result. And if you don't like the result, you look at the result, you go back, you don't have to do any more ETL. You just write another query to extract the feature and dimension. And then you can do another analysis. And this semantic data array has been deployed in the Montefiore Hospital. It's a teaching hospital, one of the biggest teaching hospitals in New York City, or Albert Einstein Medical College. And they have used this to do personalized medicine, predictive modeling, traditional translation research, all these things. It has been in production for almost 2 years now. And it works. So the next question is which machine learning algorithm? As I mentioned, after AlphaGo, that defeat this Go champion in Korea. Now, wherever I go to China a lot. I go to China, everybody talk about AlphaGo. The question is deep learning the answer for every machine learning problem? And the answer, you know the answer. The answer is no. It depends on the problem. My first case, it's actually in this Montefiore Hospital. It's the prevention of organ failure checklist, proof check. So basically, some of the patients with respiratory problem, when they develop the acute respiratory failure, they require prolonged ventilation. And a lot of time it also causes organ failure. And so most doctors, when you have a respiratory problem, you go into hospital, the doctor, especially in the US, the doctor is afraid of being sued. Why don't you do something before I have organ failure? And so doctor will automatically, when you come in, you will do intubation right away. So basically, many unnecessary intubation resulting in undue cost and pain for some. It costs money, and the patient basically suffer from that process. And the goal of this whole project is to identify patients at high risk for developing severe ARF to intervene in time. Basically, when a patient comes in, there's a way to make prediction how likely this patient is going to develop acute respiratory failure. What's likely? If I can provide some kind of indication, then doctor can make judgment. If without any indication, doctor want to protect their butts, so they will say, okay, we'll just do an intubation, make sure that the ARF will not happen. So project basically, how do we do it? Based on machine learning of patient EMR to accurately predict possible ARF to prompt clinician to take proactive steps. So instead of using deep learning, using random forest machine learning algorithm over historical patient EMR, patient with ARF, without ARF, develop into ARF, now patient with intubation, non-intubation, all this category, and then you use machine learning to build an R model and employ 5 calculated valuable and 41 covariant variable, so totally 46 variables. So when the patient come in, it will put all this information, this 46 piece of information into the system. The system will go through the model, and it will tell you that what's likely chance of this patient developing ARF, acute respiratory failure. It's like 10%, 20%. The doctor make the judgment, do I want to do intubation or not? Now, if the answer comes back with 70%, the doctor most likely, okay, should do intubation, 70%. With 20%, then, maybe I can hold out, wait until maybe, next week or next day or something like that, until if something changed over the next few days. So why use random forest? Those random, there's so many different choices. You look at the top there, there's k-nearest neighbor, on and on. Of course, everybody know about the deep learning, the neural network, support vector machine. Why choose random forest? Both random forest and deep learning work well, but depends on the problem. Random forest handle poor signal noise ratio better, more suitable, highly imbalanced data. Because in EMR, you get 1.8 million patients, in this case, 1.8 million patients. Out of these patients, probably only a few thousand have this disease, a few thousand have the other disease. So it's very imbalanced data as opposed to facial recognition or image classification. We all have 2 eyes, 1 nose, 1 eye, one mouth, something like that. So there's only small variation. the signal noise ratio is much lower. But in this case, random forest work much better. That's why they choose random forest in this case, rather than deep learning, the artificial neural network. So currently, this project is deployed at Montefiore Hospital, and basically is when a patient comes in, they will put all the test data into the system. The system will make a recommendation how likely this patient is going to develop ARF, and then the doctor can make the judgment. And now, doctor is no longer flying blind. He can make, based on that data, be able to make some good judgment. It's save a lot of money, basically. Get rid of a lot of unnecessary interpretation. And as a basic, this is a very rough estimate. Some estimate that they save about $4 million a year due to less intervention while maintaining same clinical outcome. Basically, is that, the situation did not get worse, but we save a lot of money because a lot of unnecessary interpretation has been avoided. Another case, it's Kyocera ceramic factory. And ceramic product today used in all kind of machine, especially in semiconductor. All the packaging is ceramics, and the ceramic, the manufacturing process involve high temperature, very high temperature. There's a batch furnace, the continuous furnace. Now, when these machines break down, it takes a lot of effort, a lot of money, a lot of time to fix it, to repair. So all these machines come with tons of sensor, a lot of sensor. Typically, for batch furnace, there's about 40, 80 sensor, and for continuous furnace, there's about 90 sensor. And expect so in Kyocera case that they totally has more than 100,000 sensor in all their factory, all their furnace, and they want to see collecting all these sensor data. How do I make use of all these sensor data to predict that something is going to go wrong before it happens? So the goal is to take proactive steps to prevent any accident or avoid damage to the furnace. Not only the damage to the furnace, something goes wrong, they shut down the machine, all the work in progress, all this product has to be scraped out. It becomes scrap. You have to throw away. And plus the stoppage, the time it takes to fix the problem, that really take a toll on the company profit. So they say, according to the company, look at this problem, it's the urgent problem. It's a top priority problem, need to solve this problem. So they look at some of the sensor data. Whenever they see something unusual happen, they go to see problem already happened. So the issue is they got all this sensor information. How do I predict, how do I see the problem before it happens? So I can, take some action. Maybe temperature too high, maybe pressure too high, whatever. Maybe the nitrogen they use in the gas, the pressure is wrong, something like that. They want to take action before it happens. And in our project with Kyocera, that they give out all this data. I know a lot of big companies try to compete because Kyocera is one of the biggest manufacturing in Japan. Many people want this project. There's IBM Japan, there's Hitachi, there's NEC. Everybody try to get this project. They give out this data for everybody to see what can you make out of this. There's totally about 7 batch sensor data. Totally about 40 channel for each batch. 40 channel data coming through, and then try to see if you can build a model to make prediction. So in our case, that we take one of the normal operation. The normal operation is this one. The 03A. We take that normal operation, the sensor data. We try to use machine learning to build a model, and hopefully, after we build a model, we put all the other test data into this model. You will be able to predict something is going to go wrong. And the algorithm we use is called ISHM, machine learning algorithm developed by Furnace Health Monitoring Function. ISHM is developed by NASA. People old enough here to know about it. In 1984, the challenging disaster happened. The space shuttle will launch, and halfway through it explode. And in the furnace, you got something like 90 sensors. For space shuttle launch, they got hundreds of sensors. It's impossible for somebody to grasp the big picture. So after that experience, NASA developed an algorithm called Inductive System Health Monitoring algorithm, and they have used that algorithm for all the subsequent space shuttle launch, and it's no longer a problem. When it launch, it fly to space. It may have some problem in the space, but when you launch, there's no more disaster like the 1984 Challenger disaster. So we use that algorithm instead of all the other fancy stuff like deep learning or support vector machine. We use the algorithm to build this model. And we put the test data, all the data into a system. Of course, for data 303A, it shows no drift. There's no drift there. But all the other data have some drift, especially for the first two, that's a major abnormal situation. There's significant drift. The issue is that how early does that drift happen? So we zoom into there, we see before the problem show up right there, there's already have a drift. And so we accurately predict that you get this 40 channel sensor data coming in, and you will be able to say, something is going to go wrong. You better do something about it. Otherwise, it will break down. And it happened. You actually have it accurately predicted. So for a case like this, and forget about artificial neural network, forget about support vector machine, forget about all this actually work out the best. The inductive system health monitoring function work best. So in both cases we talk about that that there's no one algorithm for every problem. Deep learning, artificial neural network work great for certain class of problem. For the EMR, machine learning, random forest work better. For this kind of problem, 40 channel of the sensor data coming out, you just don't know what those sensor data mean, what the interaction between them. The inductive system health, ISHM, this algorithm actually work much better than all the other things that we see so far. And because of that, that's why we get the project. We are doing the pilot right now at Kyocera now. The same algorithm also employ a steel galvanizing line at ArcelorMittal. Everybody know about this company, one of the biggest steel manufacturer in the whole world. And so this kind of thing is what Industry 4.0 is all about. The machine today have all the sensor information. You get the sensor information, you need to do something about sensor information. Now, typically they try to prevent problem. When problem happen, I want to know beforehand. Some other cases, you want to improve the product quality. Some cases, you want to reduce the energy consumption. All these things can use similar kind of machine learning algorithm to predict or to improve the operation. So the summary. The data analytics for the real world require effective data integration approach. We see very clearly the Watson project at the MD Anderson, that if you don't have good data integration approach, at the end, that's what kills you, not your algorithm, not your fancy, natural language processing. None of that. It's the difficult, the dirty work of data integration. And the other thing is that you need to pick the right algorithm, right learning algorithm for the job, not one algorithm for all the job. Our product, Allogograph Semantic Data Lake, is the most effective. It's being used at Montefiore Hospital and over a cluster of 32 machines. And so most effective for integrate data from heterogeneous sources, especially electronic matter record that's most heterogeneous, all kind of variety. And then we also have an analytical product provide many machine learning algorithms and exploration tools suitable for most real-world application. So again, it's not one algorithm for everything. And this is data science beyond the sandbox. So before I finish, I want to say something about our company. Our Franz company has been around for 34 years. We are the AI company already. Almost all the AI research use our platform. And now we focus on building this semantic database, doing some of these things that we'll talk about today. We have a business partner here in Hyderabad, India, Lee Semantic, and we are very excited about the fintech initiative or AP State, and we plan to, together we plan to set up an office there and try to take advantage of all this opportunity there, the FinTech Valley. Yeah. Thank you very much. Any question?
Thank you, sir. Your presentation was excellent in terms of the content which you highlighted. My question is associated with the sensor data,
Yeah.
which we received day in, day out.
Right.
Which method or maybe machine learning technique you feel good, which is associated with the time series or supervised model or unsupervised model?
Well, as I mentioned, we use the ISHM, the Inductive System Health Monitor, to build a model, and so because there's 40 channel, I mean the data. You look at those sensor data, you know it's inscrutable. You don't know what they really mean. It's an interaction between them, and that's the model supposed to predict. You put in this all in, it will show if the drift. Then there's something is going to wrong. It's going to happen. You can take a look at it, see maybe some nitrogen temperature, nitrogen pressure is too low. Whatever you need to correct. So you want to correct before the problem happens. And after again say that I give a simplistic presentation. After you predict there's a problem, then you start using decision tree, some of those old techniques to identify which channel really is the root cause that caused this drift. Because if this channel is a channel 22, and that has something to do with nitrogen, the pressure in the furnace, then you correct that problem. So, but the key is that first you have to know there's a problem. It's a problem. And
That's true.
That the model actually make wonderful prediction. You look at example, we got 7 pieces of data. We use 1 piece there, build a model. And then all the other 7 we put in, there's some small problem, big problem, it show up. It work well.
Thank you.
Dr. Yu, excellent presentation. Particularly India has got 1.3 billion population. We have a lot of complex data. I think definitely your algorithms are going to help the government of India as well as the governments of like Andhra Pradesh. And thank you for making a statement that you're going to start your operations in FinTech Valley, Vizag. Welcome to FinTech Valley.
We got an inside track. Got to take advantage of that, right?
Timing is right.
And I know Jay Chowdhury since 14 years ago, 2003. He is the guy that really never lost his enthusiasm for the state. He want to do something, make something happen. And I want to help. I want to not help you. I want to take advantage of you. And do something with my partner there, the lead semantic. Any more question? No more question? Thank you very much.